Good evening, everyone. I'm Shivam, and I'm presenting our work on inference maximizing point configurations for parsimonious algorithms. As much as the title may sound obscure, rest assured that our work is about a very simple geometric problem. All right, so let's start with the two approaches of geometry that we have, synthetic approach and analytic approach. Synthetic approach is the one developed by ancient Greeks, where we use axioms and theorems to prove equality of entities, for example, congruence and similarity, without using coordinates or numbers. Then analytic approach was developed by Descartes in the 17th century, where we use coordinates and numbers to solve many more problems in geometry. Now, computational geometry is conventionally done in an analytic fashion using coordinates and numbers. And computational geometry is a unique kind of computation in that it involves both numerical computation and combinatorial computation or discrete decision making. For example, our geometric algorithm may be computing the coordinates of points and lines, and then along the way, it may be taking discrete decisions that whether a point lies on the line or to the left of it or to the right of it. Now, these discrete decisions, a single discrete decision, wrong discrete decision, can completely change the direction of the algorithm. And this is what causes the robustness issues in computational geometry. Now, a curious question came to our mind that can we combine the analytic approach with a synthetic approach for computational geometry? And why do we want to do that is because in these discrete decisions, what if we, instead of computing these decisions numerically, what if we deduce them from prior computed things? So we deduce them or we prove them in a synthetic fashion. So that is the key motivation for this hybrid approach, to enable robust computational geometry. Now, there have been prior attempts at this hybrid or synthetic computational geometry. The earliest one is by Bukowski in 1989. Then in 1992, Knuth wrote a monograph called Axioms and Hulls, where he coined the term parsimonious algorithms for such hybrid algorithms, which never numerically compute anything that can be deduced or proven from prior computations. And there have been other works from maths and logic departments and even philosophy departments towards this hybrid geometry approach. Now, our work doesn't develop this hybrid approach. It simply analyzes the efficacy of Knuth's parsimonious algorithms. Now, what do we mean by efficacy? I'll explain it soon. So first, let's define parsimonious algorithm. So parsimonious algorithm is something that never makes a test for which the outcome could have been inferred or deduced from the results of previous tests with respect to a given set of axioms. Now, the geometric problem that is the focus of our work is to compute the order type of an endpoint set in 2D plane parsimoniously. So to define order type, first we have to define orientation relation or CC relation. So CC relation is defined for 3 points PQR. So if PQR is counterclockwise, then that PQR is true, otherwise it is false. Now the CC relation or orientation can be used for computing convex hull and many more geometric entities. Now order type is defined as the mapping from all these ordered triples to their orientations. So when we have computed the orientation for all the triples in a plane, we have the order type. So note that order type is a topological property. It doesn't depend on the position of the points. Now Knuth defines 5 axioms for CC relations. The 3 are kind of self-explanatory. PQR implies QRP, PQR implies not PRQ and non-degeneracy. Then the 4th and 5th are more interesting. So the 4th is the focus of our work. We develop an algorithm which deduces things using this interiority axiom. And the interiority axiom simply says that, let's say for this 4 points, in which one point is internal. So if we know that the orientation of the 3 internal triples, TQR, PTR, and PQT, then we know the orientation of the outer triple as well, PQR. So if we have an internal point in a triple, then that particular triple can be deduced. And if the triple is empty, it's an empty triangle, then it cannot be deduced. It has to be numerically computed. So yeah, very simple. And that is what this algorithm essentially does, this parsimonious algorithm, that it tries to deduce any triple first, and if it cannot deduce, then it computes it numerically. So to see this in action for the simplest of problem, again those same 4-point configuration, we have 4 triples A, B, C, D. The order of computation for the algorithm will be random. It doesn't know beforehand that which can be deduced and which cannot be. So let's say it takes A, B, C, D in order, and then it computes A, B, C numerically, but then D can be deduced, so it deduces it instead of numerically computation. So if it deduces it, it will be considered parsimonious. If it doesn't deduce it, then it is not parsimonious. Now it is possible that maybe it computed D first and then ABC. So in that case, all 4 will be numerically computed. So now you can see that order of computation is dictating that how many deductions we will have. And this is kind of the key thing, the key focus of our work, the efficacy analysis that I talked about. So let me define efficacy analysis. So we define efficacy analysis by 2 questions. That for a given number n, we'll have a lot of n-point configurations. So which point configuration, first of all, the first question is that which point configuration will give rise to the maximum inferences? And the second question is that among those maximal configurations, which computation sequences achieve that maximum number? So these are the two questions we have. So let's say, again, take the simplest case of 4 points. For 4-point case, we just have 2 configurations as shown in this figure. So in the left one, we have 4 triples, but all of those triples are empty. There's no point in any of them. So inferences will be 0. Nothing can be inferred from anything else. So this is the minimum inference case. This right, the diagram on the right shows the maximum inference case in which the outer triple can be deduced from the 3 internal triples. So we see that in this simplest case, we have possible sequences. So we have 4 triples. The possible sequences that the algorithm can take is 24, 4 factorial 24, and 3 factorial equals to 6 will yield maximum inferences. So for this 4-point case, it was easy to compute, but the complexity quickly explodes as we go to higher point n numbers. Now, why do we want, by the way, why we are not interested in the minimal configurations? Because minimal configurations are trivial. So when all the points are on convex hull, number of inferences will be 0. Okay. Because when all the points are on convex hull, all the triangles that we get will be empty triangles. Now let's define a few more things. Fundamental versus non-fundamental triples. So again, in that same case, we define fundamental triples. So a fundamental triple is a triple with no points in it. They are represented as delta 0. They can never be deduced and always have to be numerically computed. Non-fundamental triples is a triple with at least 1 point in it. They are represented as delta I. They can always be deduced, and we have a theorem proving this. So it's an easy theorem to prove, but it's not trivial. Note that in this case, where we are doing inferences using axiom 4 only, fundamental triples happen to be the same as empty triangles, because axiom 4 is about interiority. But if we are doing inferences using axiom 5, fundamental triple set may not be equivalent to the empty triangle set. Now, why I wanted to mention this is because this is something which we realized later on in our work, that our current problem is essentially the same as the minimum empty triangle problem in discrete geometry research, that we want to minimize the empty triangles. So if we have minimum empty triangles, we have more triangles which can be inferred, and that is essentially what we are trying to do also. So a quick glance at the problem complexity now. So for a given number n, total number of all triples or triangles will be n choose 3. Then the number of empty triangles or fundamental triangles, there is no known formula for that. Number of non-fundamental triples will be n choose 3 minus number of fundamental triples. Then number of possible sequences for deduction will be m factorial. So m is the number of all triangles. And we can see for a 6 points case that 6 choose 3, we get 20 triples, and number of possible sequences is 20 factorial. It quickly explodes. And in this table, we have shown the number of order types. So the number of order types also very quickly explodes. So for 3-point case, we just have one order type. For 4-point, we just have two that I showed here. For 5, 3, then 16, 135, and then it quickly explodes. So essentially our problem is that we have to maximize this deductions, number of maximum deductions, which will be n choose 3 minus number of fundamental triangles, but there's no no formula for number of fundamental triangles. So what we do is we suggest two constructive approaches to get these configurations which maximize deductions. The first constructive approach is forward construction, and the second is backward construction. So now I will discuss both of these approaches. So like I said, for efficacy analysis, we have two parts. First is the configurations, and the second is the sequences. So in part one, we discuss the extremal or maximal configurations. So forward construction. So forward construction is simple. You start with, let's say you want to find the maximal configuration for number n. You start with something, some simple case for which you already know the maximal configuration. Let's say we start with just 3 points, 3 points, simple triangle. Then you add a point in each of the different regions for that configuration. Then you get multiple 4-point configurations, and a lot of them will be isomorphic. Ultimately, you will get 2 unique 4-point configurations. Then you get regions in that, you add points in that to get 5-point configurations. You use isomorphism to reduce and get unique 5-point configurations. Then you go to 6, and so on and so forth. You keep doing that. So we did this by hand for up to 6-point cases. So for 4-point cases, we get these configurations. For 5, we get these 3. For 6, we get 12 or 14 type of configurations. So it becomes very difficult. We just have shown just this, the maximal configuration for 6-point case. So in this case, we get 7 inferences. So this is the 6-point case. So this is the forward construction approach. And the key idea in this forward construction is that by doing such constructions, we hope to get some insights about which type of constructions lead to maximum deductions. Okay. And we could get some insight about the possible candidates, which I will share soon, that which are the possible candidates for the maximal configurations for any general n-point case. All right. So before that, backward construction. So in the backward construction, what we do is that we assume that we have been somehow given the convex hull of a maximal point configuration of size n. Then we connect all the points with lines giving rise to different regions, and we add one point in one of these regions and see which region maximizes the inferable triples. And we keep adding more points as we go further. So for example, so we have developed a Python code for this. So let's say in this case, we add a point in this region, this little red dot. And if we add point here, we will get 4 inferable triangles. So this point will essentially lie in 4 triangles. Whereas if we add this point here, we get 8 inferable triangles. So all this process, so forward construction was done manually, backward construction is kind of semi-automated. Yet still, these are all empirical approaches, and we still do not have any conclusive answer that what will be the maximal configuration for an endpoint case. But we do have some strong candidates for maximal configurations or inference maximizing configuration. The first candidate is triangle within triangle configuration, and this candidate came from a convex hull heuristic. So a little while I mentioned that if all the points are on the convex hull, then we will, and then all of the triples will be empty triangles, and we will have no inferable triangles. So it minimizes, if we have all the points on the convex hull, it minimizes our inferences, but we want to maximize. So what if we keep as minimum points on the convex hull as possible? So the minimum that points on convex hull that we can have is simply a triangle. So a triangle within triangle configuration seems a very strong candidate, and we have empirically so far found it to be true for up to 7 points, but of course, complexity quickly explodes beyond that. So we'll have to find approaches to do the empirical test beyond that. Then another candidate is a spiral point configuration, where we do a forward construction and start placing points in an outward spiral, like we have shown in this diagram. Then the second part of our inference efficacy analysis is inference maximizing sequences. So for inference maximizing sequence, this is still very much a work in progress. So now once we have that maximal configuration, now the number of possible sequences, like we showed before, it explodes very quickly. For, let's say, for 6-point case, we'll have 20 factorial possible sequences. So the complexity of this problem is essentially order of n cube factorial. Now there are some trivial maximal sequences which we define as when we compute all of delta n before proceeding to delta n plus 1. So then we can ensure that delta n plus 1 will definitely be inferred. So this ensures that all of the triples that can be inferred will be inferred. So these are the trivial maximal sequences. So in our work, we have proven two simple properties about these maximal sequences. The first is that an inference only path always exists for all non-fundamental triples. So this is essentially the existence of trivial maximal sequences. Theorem 2 is about proving that non-trivial maximal sequences also exist. Both of these, second theorem was easier to prove. First theorem required a proof using induction, which we have shown in our paper. Although both are also intuitively easy to understand, that if you have a triangle which has points in it, it can definitely be inferred. There will definitely exist a sequence that will infer it. And this is the outline of the induction proof that we have in our paper. I'll not explain the proof now. You can refer to the paper for that. So in summary, the immediate next steps that we have now, since it is very much a work in progress, the first step that we have is that we would like to automate constructions using order type isomorphism. So that forward construction is currently being done manually, because automating that is not trivial. That is the next step that we're working on. The second thing that we want to work on is to prove that the greedy property for the construction is also globally optimal. It is not just locally optimal, but globally optimal. So when we are going from 4-point configuration to 5-point, and from 5 to 6-point, we are taking the greedy choice. We are choosing that configurations which are maximizing in that step. But let's say we have to reach up till n. If our greedy choice is also optimally globally optimal, then we can ensure that our forward construction will in fact yield the maximal configuration for point n. So the greedy property has to be proven for both constructions. That is what we are working on. Then we wish to count the maximal sequences. So for this, we are taking a hypergraph approach, which we have explained in the paper a little bit. Then future work and extensions, there are a lot of interesting things. The first most interesting thing is to use other axioms and theorems for inferences, and maybe multi-axiom inference. Because if we are using parsimonious algorithms in practice, we'll not just use axiom 5, we'll use axiom 5, 4, 5, and maybe other theorems as well. Then the second most important thing is that we would like to connect and compare it to exact computation. That what if all of the computation is done exactly? Then maybe this hybrid approach is not required. So, but exact computation is also very expensive computationally. So what benefits does our approach really bring any computational benefits? So that is what we would like to connect and compare it with. Then third is we can use neural network assisted automated constructions. So this is inspired from alpha geometry work by Google, where they trained a neural model to do intuitive constructions for high school geometry problems. And in our case also, automating the constructions is challenging because machines do not possess that geometric intuition. And so somehow maybe using neural network based approach, it is possible. So we are working on that, and we are positive about this. Then fourth one is getting tighter bounds on minimum empty triangle problem. So this is something which will be miraculous if this happens. So minimum empty triangle problem, like we told, it's an Ardo class problem, a well-established Ardo class problem, and there have been bounds, tighter bounds that have been found for this. But maybe hopefully our construction-based approach can yield an even tighter bound for this problem. All right. So yeah, that is all from our side, and now we are open for any questions, suggestions, and comments. Thank you.